For over 8,000 years, our species has woven a narrative that has attempted to describe the ontological nature of reality. A narrative that, as we've seen, appears as much in the dialogues of philosophy as it does in the natural sciences. But there is, of course, no mystery behind any of this, for, as mentioned in the opening chapters, science is itself a child of philosophy, with all forms of modern thought only being the latest in a far-reaching journey of discovery. The UK's most prestigious science academy, the Royal Society, was itself founded by an invisible college of so-called natural philosophers, who in the 1660s began meeting to discuss a new branch of philosophy that involved promoting knowledge of the natural world through methods of observation and experiment. Indeed, it wasn't until the 19th century that we began referring to these natural philosophers as scientists. Even today, our education systems offer graduates a PhD, a doctorate in philosophy. So though it may seem that these paths have since diverged significantly, we should note that even within our most cutting-edge fields of empirical study do we still find the theories of ancients being tested. So that as new reframes old, do the intuitions of old gain ever more relevance, ensuring the continuation of a dialogue that persists beyond time. However, one particular inquiry that has remained at the forefront across all ages has been our quest for universal fundamentals. A quest that poses a question which happens to run in parallel with our philosophical inquiry into the nature of being and becoming. Is nature fundamentally made of particles or waves? So, before we try to understand the elusive flux and its relationship to consciousness, let us first consult these bygone thinkers and unfold their timeless narrative so that we might better understand why it is that we ask the questions we do. So join me as I attempt to unpick the infinities of what is. It all starts with a deceptively simple question. What is light? Ask a child and you will receive a fairly confident definition regarding a level of brightness. Some children may even suggest energy or even electricity. But even adults tend to describe the nature of light in much the same way. Those of us who remember snippets of our high school physics classes may be able to recall that light is actually an electromagnetic wave. Oh wait, no, it's a bunch of photons, right? Just take a look outside, or even around the room you're sitting in. What do you see? From your perspective, it appears that certain objects are lit up, whilst others are in shadow. Our basic assumption is that certain luminous objects, such as the sun or a lamp, are responsible for emitting this light, which then travels from its source until it reflects off the various surfaces. But if this is the case, then it suggests that some invisible version of the light must also be travelling across the room, and even across the vast stretches of space, only to reveal itself when finally impacting upon a solid object. If we think about this long enough, even this simple assumption can be appreciated as quite a bizarre phenomenon. So odd that we don't tend to appreciate how unintuitive our descriptions really are. And rarely will we give any regard for how greatly our assumptions are being influenced by the last 2,000 years of cumulative discovery. Though it was the ancient Egyptians who first provided us with a description for the nature of light, with their claim that light was the act of the sun god Ra, looking down upon the earth. It is, however, quite fitting that our story shall begin ever so slightly after this, a mere hop, skip and a jump across the Mediterranean, with a group of Greek philosophers referred to as the Atomists. The philosophy of the atom is one which suggests that every sensation, be it taste, smell, touch and even sight, can be reduced to the impacts of minuscule, indivisible particles which, when combined, create all that we see around us. A universe of particles that exist against a stark and otherwise empty void. And this is the origin of the word later borrowed by modern physicists to describe the atoms of quantum mechanics. As such, one could easily presume that the atomists of ancient Greece nailed it with a hole in one. But though their hunch does resonate with the discoveries of the modern era, there was clearly much in the details left to be understood. For example, the atomists theorized that the sensation of taste might arise due to the various shapes of atoms, where a bitter taste might be the result of jagged atoms, or sweetness the result of smooth atoms. Leucippus, Democritus, and Epicurus each were said to have written much about the nature of the senses, including their own atom-based theories of light. According to what we know of their teaching, it was the belief among these atomists that sight didn't in fact arise in the eye, but instead arose from within compressed layers of atoms filling the air between the object and the observer. The image that one perceives was said to be imprinted within each film-like layer, allowing the eye to touch the echoes of surrounding objects. Certain accounts even suggested that this compression of air atoms occurred due to atoms falling away from objects, a situation that also explained why things deteriorate as they age. However, the most influential theory of light to emerge from ancient Greece was that proposed by Plato. In contrast to the atomized theory of sight, Plato leaned towards a theory of rays, and thus set the scene for the waves v particles battleground that was to persist into the following 2,500 years. But even for the greatness of Plato, there was much left to be understood. What Plato proposed was a refined version of a theory laid down before him by Empedocles. Empedocles spoke of the eye as a lantern that emitted a special kind of fire. This was a sight built upon light rays that were not caught but emitted from the eyes. This idea, along with those embellishments from Plato, Euclid, and Ptolemy, came to be known as the extramission theory of sight, which not only offered a geometrical appreciation of light, explaining the nature of reflection and refraction, but also a model of the universe that presupposed a speed of light, for the simple reason that distant mountains always appeared in our field of vision as quickly as any nearby objects did, thus suggesting that these light rays must be emitted at near infinite speeds. A fairly logical conclusion, given the evidence available. And it was at this same time that another concept relevant to our story was first put forward, this time by Plato's student Aristotle. Aristotle, like his teacher, spoke of a world consisting of 4 elements: earth, wind, fire, and water. However, it was Aristotle who further considered the void in which these elements persisted, concluding that as a fish must swim through the water, and as we move through the air, so too must the planets themselves move through some medium that fills all space. To this 5th element, he borrowed the mythological name Aether, the primordial god of light. beyond its personification as a god, ether was the name given to the upper air, being the ideal transient between the solid dome of the Earth's sky and the heavens above. Our own word, quintessential, is taken from this idea, with quint meaning fifth and essential meaning essence. And so the pieces were set. Parts, patterns and voids. Concepts that were to remain unchallenged for another 1,000 years. Whilst many people today envision the Middle Ages as being rather abhorrent, with few gains being contributed towards the human endeavour, this description rarely proves to be the case. However, it is to the east, within the burgeoning Islamic Empire, where such inaccuracies become most evident, as it was during this time that a golden age of tolerance, multiculturalism, education and wisdom began to unfold in the region. A period of enlightenment that not only fueled the Islamic Empire from the 8th century up until the 13th, but which also led to the birth of many ideas that still influence our world today. From scholarly writings on the topic of evolution 1,000 years before the birth of Darwin, to the invention of algebra, this cultural melting pot became one of history's most influential voices. Primarily because, in contrast to the guarded nature of Christian teaching adopted in the West, the holy text of Islam instead encouraged a worldly education, regardless of origin, age or source. And so, under the reign of Abbasid Caliph Harun al-Rashid, a movement began that sought to both acquire and translate teachings from the four corners of the empire, from the scriptures of ancient Greece to Egypt, Rome, Babylonia, India, Persia and China. Indeed, if it had not been for this golden period of enlightenment, we in the West may have never even heard of Aristotle. And whilst the idea of the ether, or quintessence, as it was then referred, remained a mysterious source of alchemical magic, it was in this environment that Plato's extramission theory of sight was re-examined. Abu Ali al-Hasan ibn al-Haytham is known today by many pseudonyms, not least of which the world's first scientist. Though he did earn one other honorary title relevant to our story, that being the father of optics. So the story goes that upon failing to provide his host, the ruthlessly unpredictable Fatim Caliph al-Hakim, with a viable solution to the periodic flooding of the Nile, Ibn al-Haytham, in fear of losing his life to the whims of his host's bad temper, decided that, despite his genius, he would plead forgiveness under a case of insanity. And it worked. Successfully avoiding his corporal punishment, Ibn al-Haytham was instead sentenced to the lesser punishment of a 10-year stay in confinement. However, as devastating as this was, historically it was not for naught, as it was during his time of imprisonment that he had a revelation. Within the dark confines of his four walls, Ibn al-Haytham's mind wandered, moving in and out of the present moment, as one does, until his attention was struck, taken by a stray beam of light shining through a small hole in his cell wall. Upon paying closer attention, he noticed that as this beam came to land upon the opposing wall, it cast a peculiar, yet somewhat familiar image. Though it was upside down, he realized that this image was in fact a reflection of the outside world. Whilst many of us may have simply dismissed the curious effect, Ibn al-Haytham chose to consider the meaning behind this play of light, thus inspiring an idea that came to form the basis of one of his most influential works, the Katib al-Manatzir, known in the West as the Book of Optics. From this experience, Ibn al-Haytham devised an experiment which not only introduced our modern scientific ideals of falsifiability, replicability, and evidence for causation, but which also used such evidence to provide proof for his theory that light must travel in straight lines in the direction of its source. By simply placing a pinhole in the wall of any dark space, he was able to show how light must travel in vertical lines from the upper edge of the outer sunlit image towards the inverse lower edge of the inside dark wall, and vice versa, from the bottom of the outside image up towards the top of the inside wall. Thus, by devising an experiment that restricted a path of light through a pinhole, the outside image would be revealed inverted on the opposing wall, precisely as it had done in his cell. This he called his Al-Bayt al-Muslim experiment, translating simply to dark room experiment, although it is the Latin translation of camera obscura that we derive the name for the technology that it would go on to inspire. And if this wasn't already enough, not only did he prove that light travels into our eyes rather than out of them, but he also went on to explain how the image we see is a psychological one, created within the mind of the observer. In the centuries to come, Ibn al-Haytham's Book of Optics continued to remain the dominant text on light and optics, inspiring the likes of Copernicus, Kepler, Galileo, Descartes, and even Isaac Newton in his own revolutionary work Optics, published in 1704. But it was Newton who would once again change gears in the ongoing wave-particle debate. Being the most highly regarded mind of his time, Newton, without equal, dominated the popular opinion with his own convictions that light must be fundamentally digital. Light, as he proposed, should be thought of as moving clusters of minute corpuscles, tiny particle-like bodies of light that once again floated upon a luminiferous ether. By the beginning of the 18th century, a whole suite of models took the idea of an ether as granted, and Newton was to be of no exception. His own gravitational ether was in many respects modern, as it described a medium through which the forces of light, electricity, magnetism, and gravity could persist. But as scientific as this sounds, the truth was that both the ether and our interpretations of reality on the whole had far from shed their religious foundations. The ether was still considered to be some version of the Aristotelian purity, only now interwoven with other various heavenly influences. As Newton described, the main phlegmatic body of the ether and other various ethereal spirits moved together as a type of universal vortex that was whipped up and set into motion, at first by the immediate hand of the Creator, and ever since by the power of nature. Thus, perhaps, postulated Newton, may all things be originated from ether. But beyond the views of his era, his hypothesis for a particle-like nature of light was firmly rooted in the evidence-based thinking that we today consider scientific. For example, sound, which had long been understood to move through the air in the form of waves, showcased many attributes that light didn't. Whereas sound waves can travel through pipes and around corners, light can't. But even beyond any direct evidence, there was still plenty of reason for the public to assume Newton's authority on the topic. his revolutionary insights had already revealed how white light was actually made up of all the colours on the spectrum, and that not only could white light be split into the 7 hues of the rainbow, but this spectrum could just as easily be recombined back into white light when passing through the crystal prism. A result that inspired the realization that colour must be a property of light rather than of the material objects themselves. It was also at this time that another vital discovery had been uncovered relating to the speed of light. By using Newton's new gravitational constant, Danish astronomer Ole Rømer had been attempting to predict the orbital periods of Jupiter's moon Io. But his concerns arose when these orbital periods seemed to ebb and flow outside of the predictions set by Newton's equations at various times of the year. A fluctuation that risked jeopardizing the validity of Newton's gravitational equations as a universal constant. Rømer's own moment of brilliance, however, came when he realized that the apparent variations in the results had come about as a result of the Earth's own orbit, as well as the finite speed attributed to the light travelling from Jupiter to Earth. And so, by including the influence of the orbits in his calculations, Rømer was able to broadly calculate the time it had taken for the light to travel the great expanse between the two planets, providing an almost entirely accurate speed of light. But as reaffirming as this was for Newton's theory of gravity, it did little to support his corpuscular theory of light, which was a shame, as it was not without its challenges, such as his explanation for why light might bend when passing from air to water. According to his theory, these light bodies should be subject to the same physical laws as any other projectile. And so with this in mind, he began to imagine the moment of the light's impact upon the water's surface, rationalizing that as the particle moved through the air, it would experience no net force that might move it in any particular direction. But when it closed in on the water's surface, this slight imbalance between the density of the air and the density of the water would lead to a slight acceleration, having gravity pull the particle down towards the water's surface. This then giving rise to the refraction that we experience as light's familiar bending. As an explanation, however, it required that light must accelerate into water rather than slow down. The counter to which was put forward by Newton's most notable opponent on the topic, Dutch mathematician Christian Huygens, whose theory of light waves suggested that light would slow when encountering water, though experimental evidence would not be possible until 1850, a near half-century later. Thus, it would take the efforts of the lesser-known genius Thomas Young to devise an alternative approach to the problem. Young's interest in light had come about as a result of his medical studies, though it would have initially been an understanding of sound that inspired his 1801 experiment. As sound waves, or any wave for that matter, move about the medium of their environment, they tend to bump into things, with waves inevitably crossing back through one another, an attribute that tends to cause familiar patterns to emerge. The easiest way of envisioning these is by imagining the ripples that occur when a pair of stones strike the surface of a pond at the same time. As each splash ripples outward, waves pass through one another, causing the surface of the water to amplify a patchwork of troughs and crests called an interference pattern. And it was Young's idea to seek these interference patterns within the nature of light. Like Ibn al-Haytham, Young was able to force light through a single point cut from a sheet of paper that covered a window. Then, by placing a card vertically down the centre of the hole, he further split the beam into two very small and very close equal beams of light. His thinking was that if the light did in fact move through space as particles did, then he should expect to see two distinct clumps of light, where each beam of particles came to land, just as sand would beneath the hole of an hourglass. But if light were to instead move through the holes as waves, then the two beams would disperse in equal directions, resulting in the familiar interference pattern. And to his amazement, there it was. A band of alternating light and dark lines that could only come about as the result of two interfering light waves. Irrefutable evidence that light did indeed act like a wave. And thus he had invented the famous, well, actually, at this point it was still the less famous single hole with the small card across the middle experiment. Not very catchy, I know. But essentially this was it, the famous double-slit experiment. And if you're not impressed by this, don't be downhearted, there is still a part 2 yet to come. Though sadly for Young, as popular opinion refused to detach itself from the powerful influence of Newton, the experiment would be, for the most part, dismissed. But as time passed, and technological discoveries began to compound, it was Young's experiment that stood the test of time, so that by the end of the 19th century, with the coming of thermodynamics and electromagnetism, science had entirely adopted Young's discovery. Light was undeniably a wave, but the question which remained was that it was a wave of what? Since antiquity, electricity had inspired and amused. The ancient Greeks marvelled at the attractive force generated by rubbing amber against fur, and both the Romans and Persians had devised their own form of electric lighting, powered by early forms of copper batteries contained within ceramic pots. Ben Franklin was said to have gotten himself quite wet when attempting to prove that lightning and static electricity were one and the same phenomena, which, though he did propose the key and kite experiment, it's very unlikely he ever actually performed it himself, And electricity-themed parlour tricks, such as making flakes of golden leaf leap into the air, seemingly of their own accord, kept the wealthy amused across many a drunken evening. So by the time that James Clerk Maxwell was born in the summer of 1831, electricity had already held a fairly prominent point of focus. The first traditional battery, as well as the first light bulbs, had already been invented. But much was still not yet known, for only in the decade prior had Hans Christian Ørsted uncovered the secret that electricity was capable of generating magnetic fields. The two forces, it seemed, were somehow interlocked. In fact, it was in the year of Maxwell's birth that his future collaborator, Michael Faraday, published his now famous law of induction. Faraday's experiments showed us how not only could electricity generate magnetism, but magnetism could induce electricity. Simply by moving an ordinary magnet over a length of coiled copper wire, Faraday could generate an electrical current moving within the wire. He proposed that this must be the result of the invisible field of magnetic force that reaches out beyond the borders of the magnet. However, the experiment didn't suggest that this electrical current came about simply due to the magnet's presence, as when the coil and magnet remained motionless, the electrical current would disappear. It was only when the magnet was put back into motion that the current would present itself, suggesting a very unique bond between the two forces. The electrical current's amplitude would even increase in tandem with the swiftness of the magnet's movement, and would also move back and forward in tandem with the direction of the moving magnetic poles. One evening, after completing a public lecture, 20 minutes early, Faraday chose to spend his remaining minutes openly musing. after a short freestyle of idle speculation. He made the throwaway comment that these ripples upon the electric and magnetic fields might in fact turn out to be the only thing that our eyes had ever seen. Unknown to Faraday, it was his intuition for this mysterious medium, and the understanding that Maxwell was yet to provide, that would inevitably lead to the entirety of our modern electrical civilization. Where the genius of Maxwell first enters is that it was he who devised a way of bringing these varying qualities of electricity and magnetism into a simple mathematical framework. That might not sound entirely exciting, but it was revolutionary. And perhaps far more exciting than it appears at face value, because encapsulated within 4 modest equations was the ability to describe every attribute of this peculiar causal occurrence. From the amplitude of the magnetic and electrical waves to the way they would influence one another through movement within a 3-dimensional space, and even the direction of the field and the density of the system's environment. All these subtleties and their various relationships were here outlaid in 4 short and beautifully elegant equations. But the great party trick of his life was not yet over. For his most influential discovery was to arise almost entirely by accident, when he chose to consider how his new equations might operate within the ether and the vacuum of space. Within the constraints of his theoretical void, each of the 4 equations gave a new insight. 1, that there were simply no electrical charges present within a vacuum. 2, that there are no magnetic monopoles in a vacuum. 3, that any changing magnetic field must still give rise to an electrical field. And 4, that any changing electrical field must still give rise to a magnetic field. For Maxwell, this explained how, though a system might be initially chargeless in a vacuum, each force still has the ability to piggyback off the other, thus propagating through space in the form of an oscillating wave, an electromagnetic wave surfing the ether, a wave for which he then decided to calculate a speed, thus leading to what can only be described as the ultimate Uereka moment. Said Einstein of Maxwell's moment in the sun, quote, "To few men in the world has such an experience been vouchsafed," end quote. The speed of Maxwell's electromagnetic wave turned out to be identical to the then known speed of light. For Maxwell, the astonishment was instant and the revelation clear. Electricity, magnetism, and light must all be properties of a single unified phenomenon. Light must be an electromagnetic wave. The power which fuels our homes, which holds our children's paintings to the fridge door, that makes our hair stand on end, which rips the sky apart during an electrical storm, are all one and the same force as that which allows us to see the many landscapes of a sun-filled day. Though the picture was not yet entirely complete, for if this electromagnetic wave did indeed travel through space at this pace we call the speed of light, to what background should this speed be measured against? After all, there was no reason to believe that this speed should be relative to the surface of the Earth, for the Earth too was travelling through space. It seemed that any appreciation of speed at all could only ever be described relative to the observer's frame of reference. For example, we can imagine passing a ball back and forth between seats on a moving train. Within the reference frame from inside the train, the ball moves at a nice, catchable speed. But from the reference frame, of the observer sitting by the bridge feeding the ducks, the ball is actually travelling at speeds greater than 100 kilometres per hour. But it doesn't stop there, because from any reference frame beyond the Earth, neither of these first two frames of reference are correct. But more importantly, none of the three observers can ever have the right to claim that their point of reference is the one boasting absolute truth. Maxwell, puzzled by this very thought, again fell back on the existence of the luminiferous ether. As with Newton, his ether was to be considered a true definition of rest. For these thinkers, the ether was a stage not only for light, but for all physical reality to play out upon. A truly stationary medium, thin enough to allow planets and stars to effortlessly careen through undisturbed, whilst dense enough to uphold the rigidity of these electromagnetic waves. An idea that was accepted in its entirety. So indisputable was the luminiferous ether that in 1884, physicist Sir William Thomas, known to many as Lord Kelvin, made the outright comment that there was, quote, one thing we are sure of, and that is the reality and substantiality of the luminiferous ether, end quote. All that was left was to devise an experiment that could reveal the ether to our senses. And of course, an experiment was found. The Michelson-Morley experiment was to be the defining moment in the particle v-wave argument, determining once and for all that light was an electromagnetic wave acting upon an omnipresent luminiferous ether. The idea, initially proposed by Maxwell himself, was to measure the Earth's movement in relation to this ether. Because if the ether were to be the absolute reference frame for the speed of light, then with sensitive enough instruments, we should be able to witness a slight shifting in the speed of light when our own reference frame moves either with or against the ether as the Earth passes around the Sun. And so in 1887, Albert A. Michelson and Edward Morley placed their uncannily sensitive mechanisms of mirrors and beam splitters upon a floating bed of mercury and set out to measure the time difference between two equal beams of light moving perpendicular to one another through space. One travelling one way and the next its opposite. A marvel for the time, the device was so sensitive that even the slightest impact of nearby footsteps could interfere with the results. But as the device was honed and the surrounding environment controlled, the day finally came when the device began its rotation, aligning its path with the Earth's own passage around the Sun. And then the two beams were let loose, hurtling down their unique paths. But as the data began to ring in, it was clear that no variation in light speed was apparent. The speed of light seemed fixed, unaffected by the moving reference frame. And thus, no evidence for the elusive luminiferous ether could be claimed. As such, the experiment was considered a failure. However, its actual failure was perhaps its inability to pry popular opinion away from the idea of the luminiferous ether. By the end of the 19th century, the prevailing opinion was that the science of physics was coming to its close. The ether was fact, as were all forces understood to be operating within it. Michelson himself commented that the great principles had already been discovered, and that physics would henceforth be limited only to finding truths in the sixth decimal place. All that was to be known had all but been discovered. The atom, reminiscent of ideas once put forward by the ancient Greeks, had already been discovered by chemist John Dalton in 1803, and was considered for the best part of a century as being indivisible. One of the final pieces of the cosmic puzzle. Though what was to unfold next would turn out to be nothing short of a world-changing paradigm shift. In 1897, J.J. Thomas discovered the electron. The atom was divisible after all. And at the birth of the new century, Planck's own mathematical constant was arrived at when solving for the issues surrounding the ultraviolet catastrophe, thus suggesting the quantization of energy. But even at the time, most physicists, including Planck himself, assumed that this thinking was purely a mathematical derivative, non-reflective of true nature, though it would only be a few short years before the insights of a 26-year-old patent office clerk would finally make sense of these uncomfortable resolutions, not only by redefining the universal stage of the 2,000-year-old ether, but by totally reshaping our understanding of light, matter, energy, and even space and time itself. 1905 was a year that would come to be known as Albert Einstein's Annus Mirabilis, his miracle year. By June, he had re-established our fundamentals of light. By July, our understanding of motion. By September, he had rewritten the rulebook on space and time, and by November, he had toppled matter and energy itself with his famous equation, E = mc². Within mere months, this then entirely unknown enthusiast had entirely changed the way we look at the world. The first of his seminal, though slightly dry in title, papers was on a heuristic viewpoint concerning the production and transformation of light. A paper that not only landed him the Nobel Peace Prize, but redirected our discussion on light yet again by solving a perplexing quandary known as the photoelectric effect. The predicament came about when experiments in the 19th century showed how electrons could be knocked away from various metals when hit by electromagnetic radiation, or in simple terms, when the metal was lit up by light. The curiosity compounded, however, when the kinetic energy of these escaping electrons appeared totally unaffected by the light's intensity. The amplitude or brightness of the light did show to affect the amount of electrons being released, however it did not affect the electron's capacity for being released in the first place. The only aspect of the light that appeared to have this effect was the light's frequency, in other words, its colour. If a particular colour of light, say blue, could knock the electrons away, then even the faintest beam of light would be effective. But if the colour, say red, did not influence the electrons, then it would make no difference at all how intense the light was, how bright, how much radiation and energy were emitted, the electrons would remain bound to the metals. Einstein's paper solved this issue, but not before a heretical throwback to Newton's particle theory of light. At a time when light was more than proved to be wave-like, Einstein, inspired by Planck's suggested quantizing of energy, theorized that when thinking of light as packets of energy, which he called quanta, we could more easily solve the riddle of the photoelectric effect. Because if the radiation were to be considered particle-like, then each packet of quanta would have its own unique value of kinetic energy, an energy intensity that was defined by its frequency, its colour. And so, if this individual quanta held within it the energy needed to dislodge the electrons from the metal, it would. And the brighter the light, the higher the count of quanta. Hence, the higher amount of collisions it would lead to the shedding of electrons. But in contrast, if the individual light quanta did not host enough kinetic energy, again as a result of its frequency or colour, then it wouldn't matter how many quanta got sent hurtling into the metal, none would individually have the energy needed to dislodge an electron. The upshot of which meant that light, here we go again, was not in fact a wave. But this time, it was not quite a particle either. It seemed that, for the first time, it was both. In specific experiments, these quanta, which came to be known as photons, would reveal attributes associated with particles, and in other experiments they would appear wave-like. It turned out that there was simply no rule in the book of the universe that stated that light must be either one or the other. This was something new, something unique to our understanding and experience, something we still fail to fully understand today, as can be appreciated in the clumsy language used to describe the phenomenon. A language resolved to the new norm but stubborn to let go of old perspectives. It's what we now refer to as wave-particle duality. Light is not a wave, but nor is it a particle. Some might say it's both, others say it's neither, because it's a blending of the two ideas, and yet also something wholly unique. A realization that would come to influence our entire picture of reality. But Einstein was not yet done. By September of that same year, Einstein had published his third, yet still dryly titled paper, Zur Elektrodynamik bewegter Körper, on the electrodynamics of moving bodies. A paper that was to again ask the question, to what background medium must the speed of light be measured? The answer to this riddle was arrived at when Einstein assumed that not only was light restricted to this singular speed, but so too were all things. The universe had a speed limit. The more discombobulating interplay that arose as a result of this universal speed limit was that, as discussed in Chapter 3, when any matter is either increasing or decreasing its velocity, its flow within both time and space will equally be affected. So that as we ever encroach upon the uppermost extremes of this universal speed limit, physical space will literally contract, whilst the relative flow of our time slows, countering any hopeful seizing of the limit. In accordance with Einstein's rules of relativity, no thing that hosts mass can ever successfully increase to or above the speed of 299,792.458 kilometers per second. Because if it did, not only would it require an infinite amount of energy, but at the speed of light, any distance between objects would collapse to zero, and time would essentially stop moving relative to that frame of reference. In this sense, space and time themselves do not exist beyond this speed. And in the century that followed, experiment after experiment has repeatedly confirmed that this is precisely what happens. But this is still a confusing idea, because, after all, are we not moving, as is the planet, the galaxy, and all contained within? But if we are moving, then why do we not experience this slowing of time ourselves? Well, this is precisely the point, as the effects of time dilation are not experienced from the point of view of the accelerating observer. From our perspective, time will flow as it always has, at the speed of time. But if this time dilation is not experienced from the perspective of the first person, What exactly is this time dilation in relation to? As with the question, to what background is the speed of light measured? We can equally ask, to what background is the passing of time relative? The answer is that it is relative, and hence relevant only to the other objects existing within space-time. Surprising though it may be, according to Einstein's theory of relativity, there is no space-time. The so-called space-time that physicists like Einstein so often refer to is not a physical thing like the luminiferous ether. It is simply the mathematical manifold or construct that we use to appreciate the relative differences between two unique perspectives moving in respect of one another, not in respect of space-time or any other background ether. Each particle's position within space-time is relative only to the other particles. But this is not suggesting that between these particles is merely empty space, as it is not a universe of energy floating upon space-time, but rather it is a dense bed full of energy, matter, velocity, space and time all whipped up into a single unified flux of happenings. Nothing is separate from the whole. Not matter, not even light. The energy that has given rise to the photon of light is the same energy that exists between each quanta of energy, and the same which gives rise to our physical reality on the whole. Each vantage point, each perspective from within this manifold of space-time relates its appreciation of space and time to all that is within and without it. In the century most recently past, we've come to understand this flux of the universe better than ever before. The insights of French physicist Louis de Broglie, first presented in 1923, showed us that not only does light possess an underlying property of wave-particle duality, but so too do all particles and hence all matter. And with this new idea, the world was set for the quantum revolution. In mere decades, the particle description of reality was split into 17 parts, with only 3 considered responsible for matter: the up quark and the down quarks, which together form the protons and neutrons of any atom, and the orbiting electrons. All that we encounter in our day-to-day experience of the world, everything we've ever touched, tasted or heard, has been the result of nothing more than the interactions of these 3 point-like particles. A 4th particle, known as a neutrino, which, in contrast to its siblings, careens unaffected through the bodies and planet as carelessly as any truck careens through the slightest breeze, completes our lineup of the 4 matter particles. A model beyond the insights of any single great mind. One of our species' greatest ever achievements, which we quite modestly refer to as the Standard Model. These 4 particles, fundamental to matter, are known as the fermions, a pattern of 4, which nature, for reasons currently known only to herself, has repeated twice over in more exotic forms of matter. 2 sets of copies, each heavier than the last, making all in all 12 matter particles, all of which host some element of mass. The remaining 4 non-matter particles are called the bosons. These are those that make the whole machine of the universe go. Unique particles, each representative of one of the 3 known forces of the universe: weak nuclear, strong nuclear, and of course the electromagnetic force. And it is the particle representative of the electromagnetic force that we now refer to as the photon, the elusive particle of light that we have so longed to understand. But what of the ether? And so, here now, for its final bow, re-enters our wave perspective of reality. As our latest discoveries have revealed, these most fundamental elements of matter are not mere particles. As fundamentally, they are considered the excitation of fields that permeate the entire universe. For as the photon is an excitation of the electromagnetic field, so too is the electron an excitation of the electron field, the up quark an excitation of the up quark field, and so on. 17 fields, each known to interact with the others, all unified as one singular interlacing fabric relating to itself across the entire universe as it warps and stretches along the geometry of space-time. This is the picture presented to us in quantum field theory. An ocean of 17 fields which vibrate harmoniously, exciting one another into giving rise to the concentrations of energy that we appreciate as particles. Particles that appear to pop in and out of existence as they rise from and fall back into their parent field. The final field of the fantastic 17 was theorised in the 1960s in 3 separate peer-reviewed papers, all of which described aspects of a field which, in a very crude sense, dragged upon the other fields, thus giving rise to the phenomena of mass, specifically the mass found within those elementary particles. And so, how might an experimental physicist uncover such an invisible field? Well, they'd do as nature does, and excite the field into revealing its particle. By accelerating 2 particles as close to the speed of light as possible, and then smashing them into one another, physicists can cause the necessary intensity of waves. Because smashing particles inside a collider doesn't just send the particles' inner bits hurtling about the room, revealing their constituent parts. Instead, it sets high-energy vibrations of these fields into motion, temporarily bringing into existence new particles. Such a smash should, if the theory were correct, very briefly excite this hidden field into giving rise to its sibling particle, the hidden, fleeting boson. And in 2012, at the Large Hadron Collider at CERN in Geneva, physicists announced the discovery of this very boson, the Higgs boson, and thus the 17th field of the all-impressive Standard Model. But physicists know the battle is still not yet won, as they are all but sure that there are more fields out there waiting to be discovered. More fields that intermingle and play with all that we currently see and understand as physical reality. Still remain the fields that would explain the existence of gravity, dark matter, and the dark energy thought to be fueling the universe's growth. Nonetheless, here it is, our final frame. A picture where the flux of universal energies is understood as harmonically oscillating fields, permeating the entire universe, and giving rise to light and physicality as we know it. But importantly, in respect of our own search into the ontological nature of reality, in the language of physicality at least, due to this flux, all is one. Because nowhere within our vast wealth of scientific discoveries have we ever discovered anything truly empty. The vacuum of empty space is instead full of vibrating energies, being and becoming always and everywhere. For space is not a thing we sit in. We are space. Every mode of energy, every being, every particle exists only in its relationship with other particles. And these relationships are the actuality of that space. not but mere tendrils of connections, as between all beings, becomings, waves and particles, all spaces are full. Emptiness is full of itself, as I too might sound at times. Thus, all bodies existing upon this sea of relationships are in actuality a contiguous, fluid whole, perhaps even to an infinite degree. And so this is where we have now come to sit, upon yet another of our shorelines of understanding, upon a flux proposed 2,500 years earlier by ancient thinkers and interpreted as everything from a void to a god to an interconnected dance of layers. Light, ether, matter, us and the heavens above, both beyond and within, are all but unique cross-sections of the same pulsating moment. And so, if this is modern science's current, though clearly unfinished interpretation of the flux, where, if anywhere, can we now begin to place our contemporary ideas of consciousness?